Okay, so today's video is on force field terms. So the first, we need to understand what is a force field. Force field is basically a collection of potential energy equations, and there are different kind of potential energy equation involved in a molecular system, right? The very basic potential energy form that we can think of is basically there are two atoms and they are covalently linked with each other. So this covalent bond will have a potential energy because of this stretching and compressing motion that is there in the covalent bond. So because of this stretching motion, we have okay, let me just start the laser pointer. So just because of that stretching frequency, we will have a stretching potential. So that is now represented here in the bonded terms. The second one is torsional angle. So as you know that let's say you have two atoms, and when you rotate them, and there is a covalent bond in between, and you rotate them, and because of the some groups and the back, there would be some potential involved in rotating them. They are not like free. They will not be like free rotation. There will be some potential involved. So that's torsional angle. Then dihedral angle is there. It's pretty hard to show you here in the camera, but maybe when I will explain it later, I'll use some diagrams and stuff like that. Then we come to non-bonded potentials. So in the non-bonded potentials, we have electrostatic potential, which is basically if there are two atoms, they are not covalently linked. So there is nothing that is stopping them from running away, right? So they are non-bonded interactions. And electrostatic means that they are charged particles, so they are attracted with opposite charges. So there's a term, electrostatic term for that. Now coming to van der Waals forces. So van der Waals forces are weak interactions between two two non-bonded particles which are not having charges. So we will come to all these terms in more details. So starting with bond stretching potential. So the first example, which is there are two atoms and there is a covalent bond in between. So in that case, what is the potential equation looks like, right? I'll come to the form later, but what is the potential equation looks like? So if you can, follow this line with me. So this is the line that we follow, and it goes like this. So it is called Morse potential, right? So this type of equation, or this exact kind of potential form is called Morse potential. And the other type of potential that we are currently looking at is the harmonic potential, and that's this line. This is basically a parabola. So now why I am showing you all like these two type of potential equations, because they are closely related when we look into the low energy segment. So when we look here, I'm not sure if I can zoom in. No, I cannot. So when we look closely here at this region, at very low energy region, they look pretty identical. And why do we consider even that? Because when we are doing classical simulations, we are not doing bond breaking. This kind of like high energy stuff is not happening in classical MD at least. So we approximate, as I've in the previous discussions I have talked about how everything is just guessworks and approximations. So this is another approximation that we take, and we take this because it's computationally cheap to compute the harmonic potentials, but that comes with some certain problems that we will discuss just after this. But the good part is that in the low energy regime, we have a pretty similar curve for harmonic potential and the Morse potential. Okay, so now coming to the differences between the harmonic and the Morse potential. So first difference that you can already see is that you cannot break a harmonic bond. So if there is a harmonic potential and you try to stretch two atoms apart, when they are in a harmonic stretching potential, then what will happen? They will just come back, right? You can take them to 2 kilometers apart, but they will still come back. So I think when you are thinking this from an experimental perspective, this is sounds absolutely absurd, right? That you take two atoms 2 kilometers apart and they still comes back, which should not happen, because we are working with atoms and we know that when we have covalent bonds, they should break, right? When we take them a little apart, they should break. So why is this a problem? I mean, okay, sorry. We know this is a problem, but why do we actually do that? We do that because harmonic potentials are very easy to compute in a computer, while these exponential terms are pretty expensive for like the computer to calculate at every step million times. So because as you can see that, let's say you have 100,000 atoms, right? And so 100,000 protein atoms would mean that you have at least, let's say, the first atom is bound to the second atom, the second is bound to the third is bound to the fourth, which means if you have 100,000 atoms, we can expect roughly, I think, one less than 100,000. So that's the kind of number of times the computer has to calculate the potential energy curve every single step. So how many steps we do in 1 nanosecond? That's about I think 500 steps. So that's the kind of computational effort that will be wasted on very small, like changes. So you will see when you change your potential from harmonic potentials to Morse potential, you will see your speed will drastically reduce to, let's say, how you will get half the speed or something of that sort. But I've never tried, but yeah, we can do that, right? So, what are the other differences? Firstly, I've color corrected them in a way that red means that's the problem with that kind of potential form, and green means that's a kind of advantage over that potential form. So as you can see, the harmonic potential have just one advantage, and we have rated that advantage to its best because we always use harmonic potentials. Like always means 99% times in our MD simulations we use harmonic potentials. Why? Because they are faster. Now there are problems with harmonic potential. For example, as you can see that in the low energy regime, you can that's the only part where you can compare the harmonic and the Morse potential. So think of a situation when you haven't done an energy minimization of your system, and then there is some atom that is double the bond length of a, like let's say a usual bond length of hydrogen is 1 point something Armstrong, and let's say for some reason before the energy minimization your bond length is about, let's say, 2 Armstrongs, right? So it's double the natural length of the natural bond length, right? So what will happen? You will, let's say, previously you were in this energy level, bond distance wise, you were somewhere, let's say, here, and they were the harmonic potential energy was giving you pretty accurate results because it can describe that bottom well, pretty well. But then as you have increased the bond length, which is, if this is the usual bond length, you use double the bond length, which is now you should be somewhere here. And now tell me what is the potential of this equation. So since we are using harmonic potential, we have to put a straight line. Like, let me use a pen, I think that will be better. So this is the usual bond length, and we have to use the double bond length. So let's say this is the double bond length, and if we like put a straight line, so as you can see, when this equation will go slowly up and up and up and up and up, somewhere in the infinite regime probably these two will meet. So as you can already see that just by changing the bond length from one time to just double the bond length, we are getting a potential that is infinite. So your system will crash. If you have this type of problem and you do energy minimization, your system will most likely crash. So that's a problem with harmonic potentials. Now, let me just clean it first. Where is this? Ah, erase all. Okay. Now coming to the second part, which is Morse potential. So Morse potential can describe these, bond breaking pretty well. So this part. So for example, if we just go double the bond length and we put a straight line up here to find what will be the potential. So this is the point of intersection. So then that's the potential energy that we will retrieve from the um, potential energy equation if we put this into proper equation. So that was the potential energy that you will retrieve if you use a Morse potential and the bond length is double. And you clearly see that this kind of energy is not very high and your system will still be fine because it will not crash at least. The second advantage of Morse potential is that this is the repulsive curve that is there, and the other curve is actually from the harmonic potential. So as you see, the repulsive curve is more steeper. So since it is more steeper, what does it mean? It means that if there are two bonds in a equilibrium condition, in a covalent bond, if we change the bond length and we compress them together, just by changing a little, the potential energy will be much higher, and that's exactly what we expect from a covalent bond, right? Because we know that there are two nucleuses, and if we pull these two nucleuses together, the potential energy will be high because they are having the same charge nucleus particles. So that is another advantage of using Morse potential, that because the repulsive term is more better in the Morse potential. And that's exactly the bad part about harmonic potential, is that although it gives a cheaper, computationally cheaper equation, but it cannot describe the repulsive term as good as the Morse potential. So that's another limitation that you have to bear with when you're doing molecular simulations. Okay, so next term would be, we will go into torsional angles, and then we'll go to dihedral angles. So see you there. Bye bye.